Hello everyone, and welcome to our brand new lecture. In this lecture, we will discuss another type of linked list, which is a circular single linked list. From now on, we will dive into the deep about this type of linked list. Firstly, let's quickly recap what a circular single linked list. As mentioned earlier, the circular single linked list is exactly the same as the single linked list. The only difference is the last node in a circular linked list points to the first node over here. However, in the case of single linked list, the last node points to the null, so it's not referencing to any value. But in case of circular single linked list, it points to the first node. As you see, the reference of last node is physical location of first node over here, which is 001. So it's obvious that we can perform the operations that we are able to perform on a single linked list on a circular single linked list as well. So the first operation is creation of circular single linked list. So here again, firstly we will create head and tail references, then we create a blank node and we insert some value to this node. In our case, we create this blank node over here and the physical location of this node in the memory is 001. So in case of single linked list, the last node's reference is null. But here we know that the last node reference to the first node. So in our case, this is the only node we have. So in this case, this is the only node that we have, which means that it is the first node and the last node. So it has to reference itself. So the reference value of this node over here will be itself. So then we need to assign references to head and tail, which will be 001, because 001 is the physical location of this node in the memory. So we are updating the head's reference to the 001 and this creates link between head and this node. Then we are updating the tail reference to 001, which will create a link between tail and this node. So with this, we are creating a circular single linked list, which has only one node. Now let's see what the algorithm of this operation looks like. Here, we create a method which takes one parameter, which is node value. Then we create a blank node and update the value of blank node to the value that we are receiving from the parameter. Then the next operation over here is we are setting the next reference of this node to itself, because as you see here, the next reference of this node is itself, because we have only our circular single linked list. That's why it has to reference itself. Then the next operation is we are setting head to this node and tail to this node. So as you see, the reference of head over here is 001 and the reference of tail over here is 001, which means that both head and tail reference to this node over here, because we have only one node in our circular single linked list. So from this graph, we can understand algorithm of creation of circular single linked list. So now let's use this algorithm and create a method in Python. So let's switch to Visual Studio Code and create this method over there. Alright, now here I have created a new file which is called circular single linked list file. Inside this file, I created the node. This is the node that we have from previous lecture. In single linked list, we create the same node, which includes value and the next reference. So this part of code is not changed. Then we created new class, which is circular single linked list. Here also, init function is not changed, because here we are setting the head and tail reference to null. Then I copied this function from the previous lecture as well. The only difference over here, I put this if condition inside this loop over here. You know that this function is responsible for printing the values of linked list, because by using this, we are making our life easier to see the results in our output. So let's continue to create our function based on the algorithm that we learned earlier. So here I will create a function for creating circular single linked list. So create circular single linked list. It will take parameter self and node value. Then, according to our algorithm, we need to create a node and assign a value to it. So I will create node based on the node class over here. We have node class over here. So based on this class, I'm creating node with the value in it, node value, and this node value comes from the parameter from here. Then we are setting this node to itself, because this is the only node we have in our circular single linked list. So node dot next reference will be itself. Then we need to create a link between head and this node, and between tail and this node. So self head will be this node, and again self dot tail will be this node. So with this, our algorithm is finished. We have developed our method. Here just I will return saying that the circular single linked list has been created. So let's save our code and run it. Here, first of all, I need to create instance of this class over here, circular. It will be like this, circular single linked list equals. Then by using this, I will call our function, which is create circular single linked list. The value will be 1. So I'm going to print out circular single linked list that we created over here. You remember this expression from the last lesson. So here I'll just put the name of circular single linked list. This expression over here will print out our circular single linked list. So let's run our code. So you see that our circular single linked list is created with one element, which is 1. So here, as you see that it does not return this message from here. This is because we have not printed the return value from over here. So with this, we have concluded our creation of circular single linked list. Now you might be interested what is time and space complexity for this operation over here. So as always, we will start from the beginning. So the first line over here takes O1 time complexity, because in this case, we are just creating a node in the memory. And the next part is we are assigning the node's next reference to itself, which is constant time operation, and assigning head to the node and tail to the node is also O1 time complexity. So returning this message from here also is O1 time complexity. So if we combine all of these together, you see that the time complexity of creation circular single linked list is O1. Now, what is the space complexity? And space complexity is also O1. Because in this case, we are just creating one node in the memory. So the space complexity for this operation is O1. So that's all about how to create a circular single linked list. So in the next video, let's look at how can we insert an element into a circular single linked list. So see you in the next lecture. Alright, in the last lecture, we have learned how to create a circular single linked list, and we have seen how it works in practice. Now in this video, we are going to see how insertion of a node works in a circular single linked list. Here again, we have 3 cases for insertion of a new node to a circular single linked list. So we can insert a new node at the beginning of circular single linked list, and we can insert a new node at a specific location of circular single linked list, and we can insert a new node at the end of circular single linked list. Firstly, we will look at insertion of a new node at the beginning of circular single linked list. It's basically similar to the single linked list, but here we are performing an extra step. Imagine that we have a circular single linked list like this. We want to insert a node at the beginning of this circular single linked list. The first thing that we are going to do is to create a blank node and assign a value to it. In this case, this is our node, which has the value of 6. And the physical location of this node in the memory is 444. So to insert this node before the node 1 over here, we need to update the reference of this node to node 1, which is 001. So first we are updating the reference of this node over here to 001, and this creates a link from this new node over here to the first node over here. So the next thing we need to do is to update the reference of head over here to reference to this node over here. So the reference of heads gets updated to 444, and it creates a link between head and new node. So by creating this link over here, the link between head and node 1 get destroyed. As you see, these steps are the same as insertion of new node to the single linked list. But here, an additional step is left, which is updating the last node reference to the first node. As you see, now we have the first node's physical location in the last node. So we have to update this reference over here to the physical location of new node over here. So if we update it to 444, which is the physical location of new node over here, it creates a link between last node and new node over here, because new node is our first node now. When we create this link, the link between this node 4 to the node 1 get destroyed. So by doing this, the last node automatically references the newly created first node. So with this, insertion of a new node at the beginning of circular single linked list is finished. Okay, now let's continue to look at insertion of a new node at the specific location in this linked list. In this case, the steps remain the same as single linked list. There is no difference between them. So here again, if we want to insert a node between node 2 and node 3, we are creating a new node and assigning a value to it. Now in this case, again we have a node with the value of 6 and the physical location is 444. So if we want to insert this node over here, we need to first loop from the first node and come to the second node. Then after reaching the second node, we need to update the reference of second node to the new node. So by updating this reference to 444, it creates a link between second node and new node over here. So if you have a link between second node and new node over here, the link between second node and node 3 get destroyed. So the next step that we are going to do, we need to update next reference of this new node to the node 3. So the physical location of node 3 is 22. So if we update 22 to the new node's next reference, it creates link between new node and node 3. And with this, we are inserting a new node at a specified location in circular single linked list. This is basically similar to the simple single linked list. So here we are not performing any additional step. Now let's see how we insert a new node at the end of circular single linked list. Here again, we create a blank node and assign value it. So let's say we create a new node over here and with the value of 7 and the physical location of this node in the memory is 555. So to insert this node at the end of circular single linked list over here, we need to create a reference between the last node and this node. So as a first step, we need to update the reference of last node to this node's physical location. So in this case, this node's physical location is 555, so we will change the last node's reference to 555. And by changing it, it creates a link between the last node and this node. The next step that we are going to do over here, we need to change the reference of tail. So the tail has to reference to last node. In our case, the last node will be new node over here, which is located in memory at the address of 555. So we need to change tail reference to 555. By updating tail reference, it creates a link between tail and this new node over here. So when we create new link, the old link from tail to the node 4 get destroyed. So you might notice that all these steps are the same as the steps that we used for insertion of node at the end of single linked list. But here we need to perform an additional step, because in the case of circular linked list, the last node must reference to the first node. So we have to update the last node reference to the first node, which is 001. So in this case, new node has to reference to first node over here. We know that the first node's physical location is 001. So if we update the new node's next reference to 001, it will create a link between this new node and node 1 over here. So an important point here is that if we create a new reference to the given node, the previously created reference gets destroyed. So the reference from newly created node to the first node destroys the other reference that comes from the previous last node. So this link over here gets destroyed. So with this, the insertion of a new node at the end of circular single linked list is completed. So that's it for this lecture. In this lecture, we have learned how we can insert a new node in a circular single linked list in 3 different locations. So now in the next lecture, let's combine these different cases in one algorithm to make it easier to write a method for it in any programming language. So see you there. Alright, in the last lecture we have learned how to insert a new node in a circular single linked list in 3 different cases. So in this video we will look at how the algorithm of insertion in circular single linked list works. Here our algorithm starts with 2 parameters, node and location. So the first step here is we check whether the linked list exists or not. If it does not exist, we return error and we terminate our algorithm over here. But if it does exist, we create a blank node and assign value to it. Then we continue to check the location parameter over here. So if the location points to the first location to be inserted, then the reference of newly created node is get updated to head, because right now in the head we have a physical location of first node. Once it's updated, it creates a link between newly inserted node and node 1. Then we update the head value to this newly created node and tail's next reference to the new node, because right now tail's next reference points to the node 1, which was first node before. So after performing this operation over here, we terminate our algorithm. So with this, an insertion of a new node at the beginning of circular single linked list is completed. So then we are continuing to next condition, in which we are checking location parameter again. So if the location parameter is equal to last, it means that we want to insert a new node at the end of circular single linked list. So in this case, here all we have to do to create a reference from newly created node to the first node. So we know that tail's next reference now points to the first node, so we are updating new node's next reference to the first node. So after creating a connection between new node and the first node, we need to create a connection between last node and new node. So by updating tail next to new node, we are creating a connection between last node and new node. Then we are setting the tail to the new node because tail has to store physical location of last node. In this case, the last node becomes new node. So after completing this, an insertion of new node at the end of circular linked list is complete. So we are terminating our algorithm. Then we are continuing to the next condition, in which we are checking the location. If the location is not the first and it is not the last, then it means that we have to insert an element at the middle of circular single linked list. In this case, we are looping through the circular linked list and finding the location that we want to insert a new element, then setting the new node's next reference to the current node's next reference, because in this case current node's next reference is the next node. Then we are changing the current node's next reference to point to the new node. With this, we are inserting new node between current node and next node. So after performing this operation over here, we are terminating our algorithm, because with this we are completing an insertion of a new node in the middle of circular single linked list. So with this, our insertion algorithm is completed. So here we have combined 3 different insertion cases in one algorithm. Now in the next lecture, let's use this algorithm to create an insertion method for a circular single linked list. See you there. Hi there. Now in this video, we will create an insertion method for circular single linked list. This insertion method will be created based on the algorithm that we looked at in previous lectures. So if you haven't watched the previous lecture, I advise you go to back and watch this lecture and come back to this lecture, because whatever we are doing here is based on the previous lecture. So here I will create insertion method in this class that we created in previous lectures. The only difference that I made in this class is related to this iteration to print out circular single linked list. Here the if part of code has to be like this. So if you haven't changed it in your code, I advise you to go back and change this part of code in your circular single linked list. Then after changing it, we will create our insertion function. So here I will declare insert circular single linked list. So according to our algorithm, it will take 2 parameters, which will be the value and location. So the first step in our algorithm is to check head. So if self.head is none, it means that our linked list does not exist. So I will create a message saying that the head value, the head reference is none. Then in else condition, we will proceed to our algorithm. So here we are creating new node and assigning a value to it. So this new node will be created based on node class, and we will assign the value that comes from this parameter over here. So our node is created and we assigned a value to it. Then we are checking the location parameter over here. So as we said before, if location equals to 0, it means that we want to insert a new node at the beginning of circular single linked list. So here we are inserting a node at the beginning of single linked list. So to insert a node at the beginning of single linked list, first we need to set the next reference of this node to head reference, head. Then head should reference to this node, which will be new node, because in this case head stores the physical location of first node. So by assigning to it next reference of the new node, we are creating link between new node and first node. Then we are setting the head value to the new node, which is creating a link between new node and head. Then here we have an extra step in which we need to create a link between last node and first node. Now in this case, first node is new node, so we need to set last node's next node to new node. The next reference of tail is referencing to first node, so we need to set it to new node. So by setting this, we are inserting a new node at the beginning of circular linked list. This part is same as single linked list. The extra step is over here. We are creating a link between last node and new node. So then we are continuing to check our location parameter, in which if location equals to 1, it means that we want to insert a new node at the end of circular single linked list. So here, the first thing that we are going to do, so we need to set next reference of new node to the first node. So we will set it by using tail reference over here. So we know that tail's next reference points to first node. So by doing this, we are creating connection between new node and the first node. Then we need to create a connection between new node and last node. So to do so, we'll do it like this. Tail next equals new node. And finally, we need to set tail to new node. So by doing this, we are inserting an element at the end of circular single linked list. Then we are continuing to third case, in which we are inserting an element at the middle of circular single linked list. This case is similar to the case that we created for single linked list. So here we need to create temporary node, which will be assigned head value. This is for starting from the first node. So index will be 0. So inside loop, while index less than location minus 1, here we are setting temp node to the temp node next, because in each step we are visiting the next node. Then index will be plus 1. Actually, I've explained this part in previous lecture, so I'm not going to details here. I'm just writing the code. So we need to take the next node. We know that current node's next value is the next node. So we need to assign new node to the current node's next reference. Then new node's next reference should be next node equals next node. So with this, we have completed our method. So by doing this, we are inserting a new node at the middle of circular single linked list. So here I'll just return another text saying that the insertion has been successfully completed. So the node has been successfully inserted. Okay, this is our method for insertion. So let's check how this is working. So as you remember, in our previous lecture, we have created circular single linked list in which we have one element. Here, let's try to add element in different places. So first we are going to add an element at the beginning of this circular single linked list. So here I will just do like this. Circular single linked list dot insert. First I'm going to insert 0 at the beginning. Then I'll just copy this code. Let me just copy this code and put it many times. So we are inserting at the beginning. Then I will insert at the end, which will be 2. Then one more time 3 at the end. Then let's add 2 in the, for example, second place. So let's check how this code is working. So let's run our function. You see that the nodes that we are inserting here are inserted over here. First, our circular single linked list consists of one element, which was 1. Then we inserted 0 at the beginning of this circular single linked list. As you see, 0 is at the beginning. Then we inserted 2 at the end of this circular single linked list. Then we inserted 3 at the end again. Then we inserted in the middle. You see, we have 2 over here. So it inserted these 2 after the second element, because here I put location as second. So this is how our insertion method works for circular single linked list. Now you might be interested what is the time and space complexity for this method over here. So as always, we will start from the first line. So in the first line we have if condition, which is checking head. We know that this part over here takes O1 time complexity. Then we continue to in else condition. In else condition we start with creating new node and assigning value to it, and this is taking O1 time complexity. Then we have another if condition over here in which we are checking location parameter and assigning some values over here. We know that assigning values and checking conditions are taking O1 time complexity. So this part over here will take O1 time complexity. Then we are continuing again checking the location parameter and assigning some values, updating some values over here. So this is also taking O1 time complexity because there is no iteration and any time consuming operation over here. Then we are continuing to the else part of this. So here we have created temporary node and index variable. These are taking O1 time complexity, but when we reach the loop, it takes On time complexity. We know that looping through any given collection takes On time complexity. That's why this part over here takes On time complexity, and these assignments and returning value takes O1 time complexity. So if we combine all these complexities over here, we will get On time complexity. Because we know that when we combine time complexities, non-dominant terms are eliminated. So in this case, non-dominant term is O1, so the time complexity becomes On. So insertion in a circular single linked list takes On time complexity. Then the space complexity will be O1 because we are just creating a node over here and over here, which takes O1 time complexity. The additional memory is not required to perform this operation. So the space complexity is O1. So this is all for this lecture. In this lecture, we have created a method for inserting a node in circular single linked list, and we have learned what is the time and space complexity for this method over here. So see you in the next lecture. Hi there. In this video, we will talk about how to traverse a given circular single linked list. It's basically the same as single linked list. There is no difference at all. We first start with the first node and bring out its value and keep continuing and print each value until we reach the last node. So in our case, first we are printing the first node, which has the value of 1. Then we are traversing to the second node and printing its value. So the second node is node 2 and the value of node 2 is 2. Then we are traversing to the node 3 and printing its value. So node 3's value is 3. So here we are using print statement to print it. Then we are traversing to the last node and printing its value. When we reach the last node, we stop over here. So with this traversal of circular single linked list is completed. Okay, let's see how the algorithm of traversal of circular single linked list look like. So the algorithm looks like this. So here the first step is we are checking the head. If head exists, it means that we have elements in the circular single linked list. Then we are continuing to loop through circular single linked list and print its value. Otherwise, if head does not exist, we terminate our algorithm. So this loop continues until we reach the last node. When we reach the last node, we terminate our loop and traversal of circular single linked list is completed. Now let's switch to Visual Studio Code and see how can we write traversal method of circular single linked list. So here inside circular single linked list class, we will create new method. We have created this class and methods in our previous lectures. If you are interested from where these methods are come from, so I advise you to go back and watch our previous lectures. So here at the end of this class, I will create a new method which is called traversal circular single linked list. So traversal CSLL. It will take as a parameter self. Then, as mentioned in our algorithm, we start with the first condition. In the first condition, we are checking head value. So self head is none. It means that we don't have any element in our circular single linked list. So we will print out saying that there is not any element for traversal. Else we will continue to traverse through our circular single linked list. So here, one more time, I will create temp node, which will take the head value to start from the first node. Then while temp node exists, we will loop through our circular single linked list and print its value until we reach the last node. So here I will print temp node dot value. Then we are assigning the temp node the next node, so which is the next reference of temp node. Then here we are writing if condition to check whether we'll reach the last node or not. So we know that in circular single linked list, last node references to first node. So it means that by assigning temp node the temp node's next value, the temp node will be the first node. So here we can check it like this: self_tail.next. So this means that we reach the last node and the next reference of last node is first node. So we need to break our loop over here. So I'll put break over here. So with this, our traversal is finished. So let's run our traversal function and see how it works. So here below we had code before that we created, in which we are creating circular single linked list and inserting some values in it. Here under this line I will write our function traversal. So let's run our code. You see that when we run our code, it starts to loop through circular linked list and print out its nodes values. So the first node is 0, then 1, then 2, then again 2, then 3. So with this we are traversing through circular single linked list, and when we reach the last node we stop there. So you might be interested what is the time and space complexity for this method over here. So as always we will start from the first line. You know that checking head and printing some message to output is O1 time complexity. Then we are creating a temporal node over here. This is also O1 time complexity. Then here we have loop, and we know that looping through any given collection is O(n) time complexity. So this part of code takes O(n) time complexity. Then inside loop we have if condition and some assignments over here. So these codes over here take O1 time complexity. So if we combine all these complexities, we get O(n) time complexity because non-dominant terms are eliminated. Now you might be interested what is the space complexity for this operation over here. As you see, we are just creating temporal node here, which means that space complexity is O1. So an additional space is not required to perform this operation over here. So this is all for traversal of circular single linked list. So in the next lecture, let's see how can we find a node inside circular single linked list. Alright, so in the last video, we have talked about how to traverse through a circular single linked list, and we have learned how it works in practice. Now in this video, we will talk about how to search a given node inside a circular single linked list. Here again, the algorithm is same as a simple single linked list. Let's say if we want to find a node which is in the middle of circular single linked list, we have to start from node 1 and traverse until we find the searched node. Let's say if we want to search for a value of 3, which is located in node 3, so we'll start from first node. We will check if this is the value that we are looking for. If it is not, then we are continuing to the next node. Now once again here we are checking if this is the value that we are looking for or not. We see that we are looking for 3, but in this case it's 2. So we will continue to the next node. So when we reach the node 3, we see that the value that we are looking for is located here. So we stop here and print out the value. So this is how the searching of a node in single linked list works. The problem here is circular single linked list might cause an infinite loop because when we reach the end of list, it goes to the beginning. So here we can have infinite loop circularly. To avoid such situation, every time when we visit a node, we check that node's address is equal to the tail value. If yes, this means that this is the last node of the linked list, so we terminate over here. So let's see what does algorithm of searching a node in a circular linked list looks like. So the algorithm looks like this. Here it takes as a parameter node value. So one more time we are checking head value. If head exists, we are continuing over here. If it does not exist, we terminate our algorithm over here. If it exists, we are starting a loop. Inside loop we have if condition, and with if condition we are checking if the current node is the node that we are looking for or not. If yes, we are terminating our algorithm. If no, we are continuing our loop until we find node. When we reach the last node, we stop over there because if we don't stop in the last node, then inside circular single linked list we will have infinite loop. So let's see how this is working in practice. So let's switch to Visual Studio Code and create a method there for searching a node in circular single linked list based on the algorithm that we have over here. So here, once again, we will create our function inside the class that we created in previous lectures. So this is the circular single linked list class. So here we have all our methods, creating circular single linked list and inserting a node into circular single linked list and traversing of circular single linked list. And here we will create searching for a node in a circular single linked list. So here, based on the algorithm that we see in our slides, we will create new function over here which will call search circular single linked list. So def search CSLL. As we said before, it takes as a parameter node value, and the first step over here is we check head value. If self.head is none, then we return saying that there is not any node in this CSLL. Else we will start loop through the circular single linked list. So here once again I will create temporary node which will take the value of first node which is stored in head. Then inside while loop, while temp node, we will check the value that we are looking for. So if temp node's value equals to the value that we are looking for, node value, then here we will return the value of current node, so which is temp node. Then we need to assign temp node the value of next node. So it will be like this: temp assign temp next, because in each step we are traversing to the next node. So if we run our code like this, it will be infinite loop, because we know that the last node's next reference in circular single linked list points to the first node. So without any condition over here, it will run this code infinitely. So to prevent this case, we need to put if condition over here, which will check when the node reaches the last node, it will terminate there. So if temp node equals self.tail.next, then we will return saying that the node does not exist in this CSLL. So with this our function is complete. So here in the first part of this if condition we are checking head node. If it is not exist, then we are terminating. If it is exist, then we are continuing to loop through the circular single linked list and find the element that we are looking for. If we reach the last node, we are terminating our loop over here. So let's check our code and see how this is working. So once again, I have a code over here in which we are creating circular single linked list and inserting some values in it. We see that we have the value of 3 over here, so I will use this search function to find value of node in this circular single linked list. So here I will write the name of circular single linked list and dot search for 3. So I need to print out the return of this function. So let's save and run our code. You see that the value of 3 is printed over here, which means that 3 exists over here. So if you run our function, for example, for value of 4 and run our function, you will see that it says that the value does not exist in this list. You see that the node does not exist in this CSLL, which means that we don't have any node with the value of 4. So you might be interested what is the time and space complexity for this method over here. So once again, we will start from the first line of code over here. So the first line of code is if condition over here. So we know that checking head and returning some message over here is O1 time complexity. And then inside else condition, we have created temp node and assigned head value to it. This is also a constant time operation. But here looping through circular single linked list is O(n) time complexity. Even though these if conditions over here are O1 time complexity, the whole loop is O(n) time complexity. So if we combine these time complexities over here, we will get O(n) time complexity. So the time complexity for searching a node in circular single linked list is O(n). Once again, space complexity is O1 because here we are just using one temporary node over here. So that's why space complexity is O1. So that's all for this video. So in this video, we have learned how to find a given node in circular single linked list, and we have seen the time and space complexity of it. Now in the next video, let's see how deletion works in circular single linked list. See you there. Alright, in the last lecture, we have learned how we can search for a node in a circular single linked list. Now in this video we are going to talk about deletion of a node from circular single linked list. We know from previous lectures that to delete a node from a linked list we have three cases. So this is applicable over here as well. So the first case is deleting the first node from the circular single linked list, and the second case is deleting any given node, and the third case is deleting the last node from circular single linked list. So let's look at the first case. The first case is deletion of first node. Here again we have two cases. The first case is if the first node is the only node in the single linked list. All we have to do here is to delete all references that point to node 1 over here. Here we know that there are three references that point to node 1 in this case. So the first reference is from the head, the second reference is from tail, and the third reference is this node is referencing itself because this is circular single linked list. So to delete this node from here, the first thing that we are going to do over here, we need to update reference of head to null. So by doing this, we are deleting the connection between head and this node over here. Then we will continue to update tail reference. So if we update tail reference to null, it will delete this connection between tail and this node over here. So finally, we will update the next reference of this node over here. So if we update the next reference of this node over here, it will delete the link with itself. So after doing this node is eligible for garbage collection. So garbage collector will come and destroy this node over here. With this, the first node from circular single linked list gets deleted when we have one node in our circular linked list. Now let's look at the second case in which we have more than one node. So in this case, we need to update head reference to the second node, and last node's reference has to point to the second node because in this case, second node will become the first node over here. So the first thing that we are going to do, we will update head's reference to the node over here, which is second node. So if we update it, it's creating a link between head and this node over here. So by creating a link between head and the second node, so by updating head reference to the second node over here, we are deleting the link between head and first node. This also deletes the link between node 1 and node 2 over here. So the next thing that we are going to do, we need to update last node's reference to point over here, which is the second node. So this node will be the first node if we delete this node from here. So when we update the last node's reference, it creates a link between last node and here and deletes the link between from last node to the first node. So the link is created over here. Now the first node over here becomes eligible for garbage collection. So the garbage collector comes and destroys this. So with this deleting of a node from circular single linked list in which we have more than one node is complete. So let's continue to the next case over here, which is deleting any given node from the circular single linked list. Deleting of any given node from circular single linked list is similar to the single linked list. So here, for example, if we want to delete node 3 over here, all we have to do, we have to traverse from first node and come to the second node and stop here. We have to stop here, which is the node before the node that we want to delete. So the next step over here, we need to update node 2's reference to point to node 4 over here. So by setting node 2's reference to the physical location of node 4, we are creating link between them. So with this, the link between node 2 and node 3 is deleted, and the link between node 3 and node 4 gets deleted. Now this node over here, which is node 3, is eligible for garbage collection. So the garbage collector will come and destroy this node over here. So and with this, deleting of any given node from circular single linked list is complete. Now let's continue to the last case over here, which is deleting the last node from circular linked list. So here again we have two cases. The first case is similar to the one which we had in deleting the first node from the circular single linked list. Here again, the first thing that we are going to do, we will update head reference to null. So this deletes link between head and first node over here. And then we will update tail reference to null, and this will delete the link between tail and this node over here. Then we will update this node's reference to null, and this deletes the reference by itself. So then this node becomes eligible for garbage collection, so the garbage collector will come and delete this node from here. Then the next case is when we have more than one node in our circular single linked list. In this case, if we want to delete the node over here, the first thing that we are going to do over here, we will loop through nodes from here until we reach the node that is before the last node. So in our case, node 3 is before the last node, which is node 4. So when we reach here, the next thing that we are going to do, we will update the reference of this node over here to point to the first node. So we know that the physical location of first node over here is 001. So by setting these to 001, it creates a link between node 3 and node 1, and these links over here gets deleted. So the link between node 3 and node 4 is deleted. The link between node 4 and node 1 is deleted. So the next step over here, we need to change the tail reference to point to node 3, which is the node before the last node. So by updating the reference of tail over here, we are creating a link between tail and node 3, and the link between tail and node 4 gets deleted. Now you see that we don't have any link to the node 4 over here, which was the last node. So this is eligible for garbage collection, so the garbage collector will come and destroy it. So with this, deletion of a node from the end of circular single linked list is complete. So that's all for this lecture. Now in the next lecture, let's combine all these three cases together and to create an algorithm which will make our lives easier to develop delete node method in our circular single linked list class. So see you there. Hi there. In this lecture, we will look at deletion algorithm, so in which we are combining all three cases that we discussed in our previous lecture. Our algorithm starts with the parameter of location. Then we are checking the head value. So if head equals to the none, we terminate our algorithm because it means that we don't have any element in our circular single linked list. But if head is not equal to none, it means that we have nodes in our circular single linked list, so we can continue to do our algorithm. So the next step over here, we are checking the location parameter. So if the location parameter equals to first, it means that we are deleting a node from the beginning of circular single linked list. Now in this case, we have two cases over here. The first case is if we have only one node in our circular single linked list. So if we have only one node in our circular single linked list, we know that we have three references to this node. So the first reference comes from the second reference comes from the tail, and the third reference comes from itself. So it's referencing to itself. Now in this case, if we set all these references to none, so the node becomes eligible for garbage collection, so garbage collection comes and delete this. So here, as a first case, we are setting all these references to none. Now the second case over here, if we have more than one node in our circular single linked list. So in this case, we need to change the head reference to the second node. By setting head to the first node's next reference, we are creating a link between head and the second node. Then we need to change reference from last node to the first node. So if we set the tail next to head, it creates a link between last node and the second node over here. Now the second node is our first node. Then after completing these steps over here, we terminate our algorithm. Now if location is not equals to the first, it equals to last, then we need to delete a node from the end of circular single linked list. In this case also, we have two cases. The first case is in which we have one node in our circular single linked list. So in this case, it's similar with the case over here, so I'm not going to detail of it. Here we just need to set head, tail, and first node's next reference to none. By doing this, the node becomes eligible for garbage collection and garbage collection deletes it. Then the next case over here, if we have more than one node in our circular single linked list. Then in this case, we are looping through circular single linked list till the node that is before the last node. Then when we reach that node, we are creating the connection between tail and with this node, and we are setting the current node's next reference to head. By doing this, we are creating a connection between this node and the first node, and connection between tail and this node. Then after finishing these steps, the last node becomes eligible for garbage collection, and the garbage collection destroys it. Then we are terminating our algorithm. Now, if the location is not equal to last, then we are deleting an element from the middle of circular single linked list. So in this case, we need to loop through the circular single linked list until we reach the node that is before the node that we want to delete. In this case, this becomes our current node. So we need to just change the current node reference to the node that is after the node that we want to delete. So in this case, the next node's next reference is the node that is after the node that we want to delete. By creating this connection between them, it deletes the connection between current node and next node to the other node. Then the node after the current node becomes eligible for garbage collection, and garbage collector comes and destroys. And with this, the deletion of node from middle of circular single linked list is complete. So we terminate our algorithm. So this is our algorithm for deletion of a node from circular single linked list. Here we combine all three cases to make our life easier. Now in the next lecture, let's use this algorithm over here and create a method to delete a node from circular single linked list. See you over there. So in this lecture, as we mentioned before, we will create a delete method which deletes a node from circular single linked list. So we will create our method inside our circular single linked list class, which we created before in our previous lectures. So our all methods are inside this circular single linked list class. So here I will create this deletion method based on the algorithm that we looked in our previous lecture. So if you haven't watched our previous lecture, I advise you go back and check it, because in this way it makes easier to create this function over here. So let's get started. So we will create our function like this, delete node, which will take as a parameter self as always and location parameter. Then, according to our algorithm, the first thing that we are going to do, we will check head value. So if self.head is none, it means that we don't have any element in our circular single linked list, so we cannot delete any element. So here I will print out saying that there is not any node in CSLL. So in else condition, we will continue to check our location parameter. So as we said in our previous lectures, if the location parameter is 0, it means that we are deleting a node from the beginning of circular single linked list. So here I will write a case if location equals 0, it means that we want to delete an element from the beginning of circular single linked list. In this case, we have two cases over here. The first case is if we have only one element in our circular linked list. So how do we know that if we have only one element? So we can do it by another if condition. If our tail and head is equal, it means that we have only one node in our list, because both of them are pointing to the same node. So I will write if condition like this. If self.head equals to self.tail, it means that we have only one node in our list. So what we are doing in this case, we are setting head reference and tail reference and the reference of the node to none. So by doing this, we are deleting the first node from our list. So here I will set self.head.next, which is the first node's next reference, to none. Then I will set head to none, then tail to none. So by doing this, we are deleting an element from the beginning of circular single linked list, which has only one element. Then in the else condition, we will look at the case in which we have more than one element in our circular single linked list. So in this case, what we are doing? The first thing that we are doing, we are setting the head reference to the second node. So we will set head reference to the next node. So how can we access the next node? By accessing the next value of head. So we know that head stores the first node, so by accessing the next reference of head, we are accessing the physical location of second node. So after setting this, we need to set last node's reference to point to this node over here. So we set our head to this node. So if we set tails next to head, we are creating a link between last node and the second node. So because here we set head to the second node. So with this, we are deleting the first node in our circular single linked list, in which we have more than one nodes in our list. Then we will continue to check location parameter, in which location equals to 1. If the location equals to 1, it means that we want to delete an element from the end of circular single linked list. In this case also, we have two cases. The first case is in which we have only one element in our list. So this case is similar to the case over here. So I will copy the case from here and paste it over here. Then in the else condition, we will write second case in which we have more than one element in our circular linked list. If we have more than an element in our list and we want to delete last element in the circular single linked list, so we need to loop through the elements until we reach the element that is before the last element and change its references. So how we are going to do? I will create a temporary node over here which takes the first node, which is the head. Then inside while loop, while node is not none, I will check the condition when we reach the node that is before the last node. So if this node's next reference equals to the self tail, it means that we reach the node that is before the last node. So here I will create break. Otherwise, I'm setting this node to the next reference, which means that inside this loop, every time we are traversing to the next node. With this loop, we are finding the node which is the node that is before the last node. Then after finding it, we will change the reference of this node. So the first thing that we are going to do, we will change the next reference of this node to point to the first node, so self head. Then we will change the tail reference to point to this node over here. So self tail will be this node. So by doing this, we are deleting the node from the end of circular single linked list, in which we have more than one element. Now, after checking the location parameter, here we saw that we checked for the beginning of circular single linked list and we checked for the end of circular single linked list, and we have another case in which we are deleting an element from the middle of circular single linked list. So inside else condition, I'll write this condition over here. So here again, we will start to loop through the circular single linked list. So I will create temporal node over here. So I will set this to self head as always. Then I need to create another variable over here which takes an index as a 0. Then while index less than location minus 1, which means that we will traverse until the element that is before the element that we want to delete. So here we are setting temp node to the next node, temp.next, because every time we are traversing to the next node, then we are increasing this index over here by 1. And after finding the node that is before the node that we want to delete, we will take the next node after this node. So the next node will be temp node.next. And we will create a link between current node and the node which is after the next node. So to do so, we need to set current node's next value to next node's next value. We know that next node, next reference points to the node that is after the next node. So by doing this, we are creating a link between current node and with the node that is after the next node. So in this case, next nodes become eligible for garbage collection, and garbage collection comes and delete this. So with this, we complete our method. So let's see how this is working in practice. Let's save our code. And as always, I didn't delete the code that we had before, in which we are creating circular single linked list using create circular single linked list, and we are inserting some elements to it. Now here, after this code, I will try to delete an element from the beginning of circular single linked list, then from the end, then from the middle. Let's try the first case, in which we are deleting an element from beginning of circular single linked list. So I will call delete method. Here as a location I will put 0. When we put 0, we know that this deletes the element from the beginning of circular single linked list. Now before running our code, let's just print out one more time our circular single linked list to see the difference between them. So let's run our code. You see that this is our initial version of list, and this is the version that is after the deletion. So here we created a list with the element of 0. Then we inserted an element at the beginning of this circular single linked list. We have 2 0 here. So if we delete the first element, it deletes 1 0. So if I put 1 over here, it will delete 4 from here. So if I save it and run it, you see that the last element gets deleted. Now if I put, for example, 2 over here, it will delete the element after the 2. So the third element should be deleted. So as you see, the third element deleted. So this is 1, this is 2, and this is third element. So the third element get deleted. So 2 is absent. So we can try another case in which we have only one element in our circle linked list. So if I delete insertions from here and just comment this part also for now, let me clear it. And let's run our code. We see that in this case we have only one element in our circle linked list. So let's run our function for this list over here. So for now I will put, for example, 0, which will delete first element. So if I run it, you see that initially we have one element, now we don't have any element. If I put here 1 also, it will be the same case. So if I put here 1, you see that 0 gets deleted. So our function works perfectly. So now you might be interested what is the time and space complexity for this method over here. So to make our life easier, let me close the terminal from here. And let me just make it little to see everything in the one window. So now it looks okay. Now as always, we will start from the first line of this method. So the first line of this method is we are checking the head value. We know that checking head value and printing some text over here is O1 time complexity. So the first part of if condition takes O1 time complexity. Then we are continuing to the else part. In else part, one more time we have if condition over here, and we have another if condition inside this. And inside this if condition, we are just updating the references to null. This line separately takes O1 time complexity, so if you combine them, it will take O1 time complexity. And this else part also takes O1 time complexity, because here, once again, we are just updating reference. Then we are continuing to the part over here, in which we are checking the location parameter one more time. And inside this if condition, we have another if condition, which is just updating the references. So as mentioned over here, this is O1 time complexity. Then in else condition, we are creating a temporary node, which is taking O1 time complexity. Then we have loop over here. And we know that looping through any given linked list takes On time complexity. So the time complexity of loop over here is On. Then outside the loop, we are updating the references again, which takes O1 time complexity. Then we continue to the last else condition over here. In last else condition, we are creating a temporal node one more time, and we are creating a variable. So this part over here takes O1 time complexity, because this operation is not time consuming. Then one more time we have loop condition over here. So looping through linked list is On time complexity. So this part over here takes On time complexity. Then after loop, we are just updating the references. So updating references takes O1 time complexity. So if we combine all complexities over here, we will get On time complexity, because in this case, O1 time complexities are non-dominant terms. So we have 2 On time complexity over here. This means that the time complexity for this method is On in the worst case. Then the space complexity for this method is O1, because here we are just creating 2 temporary nodes. The one is over here and the other one is here. So creating 2 temporary nodes does not take an extra space in the memory. So that's why the space complexity is O1. So this is all for this lecture. So in this lecture, we created a method which deletes a node from a circular single linked list in 3 different cases. Hopefully everything is clear. See you in the next lecture. Alright, in the previous lecture, we have looked at deletion of a node from a circular single linked list. Now in this video, we will look at how to delete entire circular single linked list, and we will implement it in practice. The steps are very simple, because all we have to do here is to delete 3 references, which are the reference from head to one node. We need to delete this reference from here. The second reference is we need to delete reference from tail to last node, and we need to delete a reference from last node to first node. So by setting these references to none, we can delete entire circular single linked list. Let's see how this is working. So if we set head reference to null, it will delete the link between head and first node. Now in this case, first node will not be deleted by garbage collector, because here we have another link which comes to the first node. So the second link that we need to break is we need to set last node's reference to null. So by doing this, we are deleting reference between last node and first node. Then first node becomes eligible for garbage collection, so the garbage collector can come and destroy this. Then after destroying the first node, it continues to the second node because there is no link to the second node, so it can be deleted. So it destroys the second node as well. Then it continues to the third node. Here again, we don't have any link to this node, so it can be deleted. So it's deleted by garbage collector. Then when it comes to last node, it cannot be deleted because we have a link to this node over here, which comes from the tail. So we need to set tail reference to null to delete this link over here. So by setting tail reference to null, the link between tail and last node gets deleted. So after this node over here, last node, becomes eligible for garbage collection. So garbage collector comes and destroys this as well. So by doing these steps, we delete our circular single linked list successfully. Now let's see how this is working in Python. So let's switch to Visual Studio Code and create a method there. So here inside our class, we will create new function over here, which is the under delete node function. So here I will create new function. I'll call it delete entire circular single linked list, and it will take as a parameter self, which is by default. Then here first we are setting self head to none. Then we need to update the last node's next reference, so we will do it like this: tail next equals to none. Then we will set tail to none equals none. So with this 3 lines of code, our function is finished. So if we run our function now, we will see that it works perfectly. So one more time, I have a code over here which is creating circular linked list with one node. If you want, we can insert elements here. If you don't want, you can just delete these circular links from here. So if we run our function for this circular linked list over here, you see that it will be deleted. Delete entire circular linked list. So to make things clear, I will just copy this and paste it here to see the linked list after deletion. So if I run our code, you see that when we create a circular linked list, we have one element over here. So by calling delete entire circular linked list, this element gets deleted. So if we just insert few elements over here, for example, I will do it by calling the insert method. So here I will put, for example, 1 in the last position. All of them I will put in the last position like this. Then, for example, let's put it 2, then 3, and save and run our code. You see that initially we have 4 elements in our circular single linked list. Then after deleting, we don't have any nodes, so it deletes all nodes from there. So now you might be interested what is time and space complexity for this operation over here. So once again, we'll start do it by line. So in the first line here, we are setting head to none, which is constant time operation. And in the second line, we are setting the last node's reference to none. This is also a constant time operation. And in the third line, we are setting tail to none. This is also a constant time operation. So if we combine these, we will get O1 time complexity for this method over here. Now the space complexity is O1 because here an additional space is not required to perform this operation. As you see, we are not creating anything over here. We are just deleting the nodes. So this is all for this lecture. Here we have learned how can we delete entire circle linked list. See you in the next lecture. Hi there. Now in this last lecture of circular single linked list, we will look at time and space complexity of operations on circular single linked list. Now we will start with the first operation, which is creation of circular single linked list. So the creation of circular single linked list takes O1 time complexity because here we're just creating references between head and node 1 and node 1 from to itself and node 1 from to tail. So this takes O1 time complexity, and the space complexity over here is O1 because here we are just creating one node. So creation of one node takes O1 space complexity. Now the next operation is insertion operation. Insertion operation in the worst case takes O(n) time complexity because, for example, if we want to insert an element at the off-circular single linked list, we need to loop through this list over here until we reach the last node. So after reaching the last node, we need to update the reference of last node to point to the new node that we are trying to add. This in worst case takes O(n) time complexity. So the space complexity one more time is O1 because here we are just inserting one node at the end of circular single linked list or in the middle of circular single linked list. Now the next operation is searching in circular single linked list. Here, as I said before, we are using linear search. So linear search means that we are visiting each elements one by one and comparing for the value that we are looking. So if you are looking, for example, for the value of 4, we need to loop through node 1 and node 2 and until we reach the node 3. So in each loop, we are checking the value of node with the value that we are looking for. So to find the 4, we need to visit all these nodes over here. So in the worst case, this will take O(n) time complexity because the value that we are looking for might be at the end of circular single linked list. The space complexity for this operation is O1 because here an additional memory is not required. Now the next operation is traversing. So we know that traversing through any given collection means that we are visiting each and every element of this collection until we reach the end. So here, when we traverse through circular single linked list, we are visiting each of elements of list until we reach the last node. So this takes O(n) time complexity. And the space complexity here also O1 because no additional memory is not required and we are not creating anything in the memory. Now the next operation is deletion of a node from circular single linked list. So deletion of node can be in 3 cases. We can delete a node from beginning of circular single linked list. We can delete a node from middle of circular single linked list. And we can delete a node from the end of circular single linked list. Now, if we delete an element from beginning of circular single linked list, this takes O1 time complexity. But when it comes to middle and the end, it takes O(n) time complexity because each time we have to traverse through the circular single linked list until we reach the node which is located before the node that we want to delete. So for example, if we want to delete last node, we have to traverse from the beginning until we reach the node that is before the last node. So this takes O(n) time complexity. And the space complexity here also is O1 because here we are just deleting an element from circular single linked list. Now deletion of entire circular single linked list takes O1 time complexity because in this case we are just updating 3 references. First we need to update head reference and this breaks a link between head and node 1. Then we need to update last node's reference and this breaks the link between last node and node 1. Then at the end we need to update tail reference. This breaks the link between tail and last node. So by doing this, we are making these nodes over here eligible for garbage collection and garbage collector comes and delete them. That's why this takes O1 time complexity because here we are just updating the references. And the space complexity obviously is O1 because here we are deleting all elements of circular single linked list. Now this is all for this lecture, and with this lecture we are completing circular single linked list. Now from the next lecture we will start another type of linked list which is double linked list. So see you over there.